Good morning and welcome to this video from Semiconductors, class 12th physics. This question is from Bihar board. Bihar is a state in India and the quality of paper is incredibly conceptual. Okay, it's very nice and the questions being asked are really conceptual in nature. And I picked up this question because this fundamental question, is related to a very important topic in semiconductor, which is formation of depletion region. Okay, so if you read this question, the question is about equilibrium in the p-n junction diode. So there are four choices given, and if you read it carefully, the emphasis of the answers is on diffusion and drift currents. Okay, now if you have done the depletion region in detail, that means you really understand the formation of depletion region, you can answer this question. Otherwise, it's a very tricky type of question. And therefore, what I thought was, instead of just giving you an answer directly, I will make you understand how the depletion region is created. And this video will remove a lot of doubts from your mind pertaining to the formation of p-n junction and depletion region, and many doubts will get cleared from your mind. So therefore, don't treat this video as just an answer video. This is an explanation video, and it will bring immense clarity in your mind about the depletion region. Okay, let's start with the fundamentals. And if you can watch my previous videos on the semiconductor devices, nothing like this, but I will just start with how this whole story works out. Okay, so let's draw this diagram and let me explain you. Okay, so I'm just building up the answer to this question, but I will do in a very explanatory term. So watch this video very carefully. Okay, so you have an n-type semiconductor. You know about semiconductors, n-type. You have donor ions in that, right? And you have excess electrons in them. So this is the n-type semiconductor. A pentavalent impurity is added, which is something like phosphorus. And then you have the other type of semiconductor, which is a p-type of semiconductor, right? So let's say you have a p-type of semiconductor, right? And I hope you understand. We talked about acceptor in this, right? So you have a donor level in N, and on the P side, what you have is the acceptor, right? So go through how conduction happens in N type, how conduction happens in P type, just for your knowledge. You don't need to know here, but you pick up two two semiconductors. One is N type, the other is P type. Now, if you notice in N type, you have, so first of all, understand that in n-type, when we draw the diagram, okay, when we draw the diagrams, what we show is this, the impurities, okay, the impurities. So if you notice, we add phosphorus. So what you show here is phosphorus. Okay, so let me just draw a sample diagram of n-type. What I'm showing you is phosphorus. Remember that. I'm not showing you the silicon anymore, because in n-type we're always worried about the dopant, which is the impurity we added. So when I show you n-type, right, I am showing you the dopant. Okay, so these are the dopants being referred to. This is a phosphorus. Okay, and then what I'm going to show you here is the electrons. Okay, and let's use colors. So say, for example, every dopant gives you what? It gives you a electron. So there is an excess electron coming from the dopant. Okay, so you can see the excess electron being represented. So these are the excess electrons, and this is what makes it negative, right? So this is the excess electrons. And we are studying this experiment, or at minimum of 300 Kelvin, where some concentration of N does appear. And then let's show, you remember, right, the minority in this is some holes. So you have minority carriers like holes also, but they are in minority, right? So an N type has excess electrons. What you see as a circle is essentially the dopant, which is, for example, it could be, so this is, for example, phosphorus, okay? Phosphorus, right? And phosphorus is P5 plus, right? So the electron, which is a valence electron, jumps to the conduction band, right? And that is what you see. So this is the pink dot that you see is, okay, let me just enlarge the view so that you can see it more clearly. Okay, so let's see this. Okay, and the green color you see is holes. Now let's go to the P side of things, right? So if you go back to the P side of things, let me draw on P side again. I'm going to draw dopant. I will not show silicon in this, okay? So let me just draw the diagram on the P side. And so I'm, for example, using boron as dopant. So I'm drawing boron, and let me just do it quickly to save some time. So these are borons, okay? Borons, and we are drawing at a very atomic level. So these are the boron impurities being shown to you. Okay, so this is boron, boron. All these are boron impurities. And if you remember, boron, works is not going to donate anything. It is going to accept actually, right? So n-type donates electron, whereas in the case of p, there is an acceptor level of energy, and you can read about it. uh, One of the videos I have is on how n-type semiconductors conduct, go through that. Okay, so let's look into the situation here. Now, the situation is very different. This has excess holes, right? And I told you holes are green, so you can see a lot of holes in a in this type P type of semiconductor, right? So I'm just drawing the holes, and you so on and so forth. So I will not waste time on drawing each of the holes. So point is a lot of excess holes present which are moving around in the lattice. Okay, they're moving, they're not stationary, and they're moving. So this is your p-type, and remember that p-type has small number of electrons also. So I'll just show some minority carriers as electrons, and you know that they move in a separate different direction, opposing direction actually. So what we have just done is, what we've done is we have an n-type semiconductor, and then we have a p-type semiconductor, right? Now what you do is you bring them together. Okay, so what you do is you bring them together, and let's see when you bring them together what happens. Okay, and we are doing that question that I just showed you, the multiple choice question, but I'm doing it in a very explanatory, I'm trying to explain it to you what goes on inside. So I'll just draw the smaller pictures because it takes a lot of time to fill the holes. All right, so let's draw the diagrams. Okay, and now what I'm doing is I'm joining these to N and P. Okay. And don't go by this, there's a manufacturing process of joining these two. I'm just showing you the larger picture, which is, you just join them. But there's a manufacturing process. Now, when you connect these two, and let me draw some impurity atoms in this. So this is the impurity atoms. These are the impurity atoms. Phosphorus, for example, pentavalent. All right, so forth. Okay, and let me draw boron on the other side, which is so this is, I'm using N on this side, and I'm using NP on this side. So this is a NP semiconductor. Okay, and I will tell you what happens. So you have this, and so on, and so you can just fill this up. So this is P side. So this is the trivalent impurities which are being shown in the form of those circles, and these are the pentavalent impurities. And let's draw the diagram. So this has electrons, right? So this has a lot of electrons in it. There's a lot of electrons going in it, and some holes also in this, right? But these are in minority. We have already seen this. And I will do the reverse on the other side. So some electrons which are minority and a lot of holes on the other side of the table, right? So this is hole, 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 and these are holes, right? And so these are the holes which are there. Now what happens is, if you notice the the P side, okay, the P side has a lot of holes and N side has a lot of electrons. So electrons get attracted to the right side. So this is what happens, and I will just enlarge it. Okay, I will just start. I will show you what happens the moment you can see a charge gradient. What is a charge gradient? Left hand side has too many electrons, the right hand side has too many holes, right? So you have a negative side and a positive side coming together. This in physics is called as a charge gradient. Okay, so some type of slope getting created, like for example, you have a ball on an incline, right? So this is a gradient, right? What is the tendency of this ball? This ball would like to come down. So we say there is a, because of the existence of a gradient, which is a slope, the ball wants to come down. And therefore, if you look into this diagram of NP, which I've just drawn, what would electrons like to do? The moment the electrons, they see the positive side. So they see a lot of positive, here, a lot of positive, because a lot of holes are there. And the holes on the other side see a lot of negative because of the excess electrons. So there is a gradient of charge that has got built up. Now what happens is this electron, would like to move towards the right. Okay, so this electron would move towards the right. And this electron also wants to move towards the right, so on and so forth. Okay. And if you notice the holes on the left hand side, the holes on the left hand side also want to move here, right? So they have a tendency, because of the, I told you, there is a gradient of charge that exists. So the holes want to move towards the left hand side. Now what happens is the junction that you've created, okay, this junction, the joining points of the two N type and P type. This is a manufacturing process, the way it is manufactured. For our class 12 physics, we don't need to worry about it. It is assume this is just connected. And once this is connected, the movement of charges, from both the sides start. So the positive charges want to move towards negative, okay? And the negative charges want to move towards the positive. Now, once they start moving, on the both the sides, this is finally a sort of current has started flowing within, the NP semiconductor, which is called as a diode. Uh, Current has started already moving. Okay, now the current moves, and this is what happens. Okay, let me show you what happens after a certain while. This is the figure you will see. Okay, and I will just draw a smaller one because it's pretty time consuming to see this. So this is the situation, and I have further reduced the size. So I will just make it, slightly less time consuming. This is what happens. So you have seen this diagram, and assume you have, the negative on the left, a lot of negative charges on this side, and a lot of holes on the other side, right? And there is a tendency for them to move towards each other. After some time, this is what will happen. You will find that, okay, I'm just redrawing. I just drew the smaller component so that you can understand what's happening. This is what will happen. Okay, this is what will happen. you will see a formation of this. Okay, a formation of this. A band will appear. Okay, this is obviously not visible to the eyes, but this is what happens. The electrons that move towards the right, what they do is they leave the, if you remember, the N side has a lot of donors, so it leaves behind a lot of uh, positive ions, which is phosphorus positive ions. So these are phosphorus positive ions. Okay, and then the other side has the boron negative ions. What I'm drawing now is boron negative ions. Okay, so this side has, so if I just enlarge it, okay, let me just enlarge it so that you can see it more clearly, and I will just label it, and these will become easy to see from the bare eyes. Let's I think for you can't enlarge it further. So anyway, so let's look into this part of it. So this is your positive phosphorus one. Okay, so this is also positive. This is positive. This is positive. So, and the other side has become negative because this side is boron. So these are the negative ions, that get created. So this is negative, 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 negative. Okay. So let me draw. So this is an interim diagram. Let me draw what happens after some more time, and so that it gives you more sense of what's happening. This was a very small diagram, maybe not clear in your minds, but I will draw something which is more easy to understand and look through. So let me draw a bigger one. And all right, so now I've just drawn an enlarged diagram. It is not very crowded. It's easy to understand. So on the left hand side, what you see is the N side, and now the electrons, entered through the junction. And now what has happened is in this particular region, which you see, okay, I'm just labeling it now. This region, which is the band you see, in the middle, this region, this is the region where the electrons that came from the left, these are the electrons which were attracted, and there were holes on the right hand side that got attracted. What happens is they, when they cross the junction, if you go and look into the previous diagram, I had a junction. A process called as recombination happens. Okay, recombination. So the cancellation effect of a hole, and so recombination of electron and hole. This is what happens. They recombine, and what is left behind is a phosphorus positive ion, which is immobile because the electron and holes have neutralized each other in this band which you see. Okay, so what you're left with is a positive phosphorus ion and a negative boron ion. These are immobile, by the way, they don't move, right? So this is your positive phosphorus ion, and what you see within the band, this is called, this is the boron ion, which is the negative ion. So this is negative ion, it is a boron ion, right? This region where this recombination happens, right? The physics terminology is, this region is called as the depletion layer or the depletion zone. Okay, this layer which I have shown, I will just label it for you again. So this particular place is called as the depletion layer or the depletion zone, where the electrons came, so the holes, these holes, because of the charge gradient, got attracted to the left, and the excess electrons. So what is left behind is this. So you see these are the phosphorus ions with the N type. These are, right. I have not used PN, I have used NP. It is one and the same thing actually. for the purpose of this explanation. So don't worry if you see Pn or Np. Okay, so this is the excess electron side. So what these are the positive. These are the phosphorus ions, and on the and these are the electrons which I'm showing you. This is the electron, the excess electron, which a pentavalent side has, right? So the pentavalent side, and this is of course the trivalent, which is your boron. And on the right hand side, you have the P side, which is the lot of holes which are available. Okay, so these are the holes that get created on the P side semiconductors. Okay, so these are the holes being referred to available on the P side, right? And you can see there's a recombination that happens. There is no excess electron or hole in the depletion region. So let me just label it. So this is your, okay, the depletion region, okay. And you can see on the N side, what you have is positive charge. I will just correct the last also. So what you see on the left side of the depletion region, you have positive charges. So an electric field is set up, and you can see this is, some kind of positive and negative available. So you have, what you're studying is now the electrostatics. So you have static charge in the depletion region. This is what you're studying now, electrostatics. All right. I hope this is making sense. There is a depletion, there is electrostatics, there is also a potential difference which has got created, from, this is the positive side of the potential. Let me just draw an artificial junction here, and so you can divide the whole diagram into two parts, so there are two parts to this. So there are two parts to this. So you can see the left hand side has the positive potential because it has positive charge. So this is the positive potential side, and this is the negative potential side. Okay, I'm giving you details, okay, because these are the questions that they ask you in examination, and if these details are not understood by you, you will get struck, because this level of detail is what the questions are all about. And then of course I told you there is an electric field which is existing here, okay. And so the electric field exists across the depletion layer, right? This is the way you represent it. And there are no holes and electrons in the depletion. So if you see this layer, this particular layer, I'll just show you this layer which I'm referring to as this particular zone, from here to here, you know, does not have any uh, excess electrons or excess holes. But if you see this particular band, this has excess holes. And if you see this particular band, which is the N side, it has excess electrons, right? And this is your holes, right? Now, when the charge carriers move, across the junction. So you have this junction, right, which I drew as an artificial line as, so this is your junction, right? This is your junction line, right? And on both the sides, you can see electrostatic charge. When these holes were moving, in the previous diagram towards this side, and the electrons were moving towards this side, I told you a current gets set up. That current is called as the diffusion current. Okay. And I'm gradually focusing on the question. Our question was what? Our question was based on diffusion current and drift current. Okay. And we will understand. It said question was on equilibrium. So when the junction is getting created, there is a movement of electrons towards the right, and that current is called as diffusion current. Okay. And diffusion current is because of the majority carriers. Okay, majority carriers on that side. So if the holes are moving, they're moving, the holes are in excess on the P side. So P side has excess holes, right? These are excess holes which want to move towards the left. The moment you bring N and P together, and the electrons want to move towards the right hand side. And finally, what happens? This is what happens. There is a depletion region that gets created, and the depletion region has power that this particular positive charge which you see, right, the positive potential side which I drew, I will just show it to you again so that you can identify easily, right? So this particular whole this positive layer becomes very powerful, and it will not allow any holes now to move towards it. So the holes are on the right hand side. These holes are not able to move. These holes, they want to move, but they cannot move because they get a repelling force from this positive electrostatic charge. And similarly, the other side, I will just show you the other side of the junction region, which is the potential, negative potential side. This side has now immobile negative charges. Now, this side also has immobile negative boron charges. These boron charges are negative. The electrons that want to move on this side, like this, these electrons cannot move because of the negative side. So at this point, you have a situation where further diffusion cannot happen. Okay, but initially, when you just join the conductors, a lot of diffusion starts happening, and gradually the depletion starts happening. Depletion is nothing but a recombination. This is what happens, and finally you have a depletion zone or the depletion region which gets created, which you see as a central band where I have written electrostatics, and formation of electric field happens, right? So this is the electric field that has got created, okay, E. And there is a potential difference between the from here to here, right? I hope you have studied the concept of potential gradient, right? You can see one of the videos on electrostatics. Potential gradient is an important concept, and the potential gradient tells you, E is equal to minus dV by dx. But let me not focus there today. I hope this till now the situation is clear. So you know what is a diffusion current? It is because of the majority carriers on each of the sides. There is a formation of junction potential and stuff like that. Now let's pay our attention to something else also. Okay, and this is very interesting. This is what will help you understand the answer of this question, which is from the Bihar board. Okay, the Bihar board question is based on this concept. Okay, so far we have just discussed the formation of depletion. So if you remember, the left hand side, which is the N side, had electrons, but it also had some minority carriers which are holes. Okay, so look into the holes. The left hand side had minority carriers. So while N side has electrons as the majority, the holes are in minority. And similarly, if you go to the other side, which is the P side, there are some electrons here also. Okay, these are in minority. So these are electrons, but they are in minority. Okay, see the electrons, right? These electrons which you see as minority electrons. Now I'm not referring to majority. The majority stuff is over. Okay, but parallelly, this is something what is happening. As the diffusion current starts building up because of the attraction and the electrostatic charge appears here, the minority carriers on both the sides, the minority. So this is minority on the left hand side, on the N side, a hole, they also start getting attracted towards this charge. So this hole, if I'm referring to this hole, will get attracted to this charge and will move across, right? It has no problem in moving towards the negative side. It is getting attracted. These are minority carriers being referred to. And similarly, the holes on the right hand side also, they are in minority, but they also move. The hole is getting attracted to the negative side, right? So this was the negative side, right? The N side. So the holes are getting attracted to the negative side, and the so the holes and the electrons on the right hand side. These electrons on the right hand side, which are in minority here, are getting attracted to the positive electrostatic charge here. This particular current, which is created because of the minority charge movement, is called as the drift current. Okay. A situation arises when the amount of drift current, okay, the drift current and the diffusion current. So the drift current, I drift, okay, I drift, which is due to the minority conductors becomes equal to the I diffusion, okay, which is the majority. Okay, this is the situation, which is the situation of equilibrium. Okay, equilibrium. And if you see it, so we have understood the word equilibrium. Now, during equilibrium, if you notice, the diffusion current has become equal to drift, and the direction of the current is reverse, which means the diffusion current is flowing in a direction, which means the excess electrons move from left to right like this, and the excess holes move from the right side to the positive side, which means the overall direction of the current was like this. Okay, so this was your diffusion current. Electron is moving in this direction, majority carriers, holes are moving towards left. So overall current direction, I diffusion, is this, right? This is your diffusion current. But if you notice the direction of the drift current is because of the electrostatic charge which gets accumulated in the depletion region, right? So the drift current is in opposite direction. The holes, which are the minority holes, are getting attracted to this negative charge, the ions, immobile boron ions, and vice versa for the excess, or so to say, the minority charge carriers on the p side. So electrons are getting attracted to the phosphorus ion. So the direction of the current is reverse in the case of drift. So drift and diffusion is happening parallelly, but they are in different direction. The net current that flows is zero at the position of equilibrium. So no current is flowing, and the circuit is open circuit, which means there is no external bias or forward bias or a reverse bias. It's an open circuit current with no battery applied to this. So if you see the choice number C, the choice number C is the correct answer for this problem. So we had to go through a complete cycle of understanding. Otherwise, you cannot answer this. If you don't understand what is the junction creation, how the diffusion current flows, and what is a drift current, and mind you, there is absolutely no involvement of bias. There is no forward bias, reverse bias. This is just 300 Kelvin plus temperature where something is happening on its own, and there is a creation of a junction potential, which I explained you, the electric field that is getting created. All this is happening together. Diffusion is happening. The majority carriers are getting attracted. The minority carriers are also getting attracted because they see the oppositely charged region getting created. Once this I drift becomes equal to I diffusion, we have a situation of equilibrium. I hope you liked this video. And if you did, please subscribe to my channel. You will see some fantastic explanations on this channel, which will clear all your doubts pertaining to semiconductors. I have videos, 2000 videos on this channel. Please see each one of them and you will find a lot of concept, a lot of solved numericals, a lot of theory being explained to you for class 11th and 12th. And the level is, if you're a student of AP Physics, SAT Physics, you're in India, you're in United States, Philippines, Algeria, Pakistan, wherever you are, you'll find this very, very, very beneficial. Thank you very much for your time, and do subscribe to my channel. Thanks.